Okay, so today, hello and welcome everybody to today's webinar for NanoExplore. My name is Judith Friesel from Jodas Group. We lead on the dissemination and training for the NanoExplore project. Before I hand over to my colleagues from the project, I would just say a couple of organizational points. So as you know, by now everyone is muted usually in a webinar. You can use the chat function in the side panel if you have any questions, and we would like to answer those questions at the end if there are any, or after the webinar if there is no time. The webinar will go on for about an hour, I would say. And of course, you will also receive the slides at the end. So today I've got colleagues here from project partners from Alcon, Ramen, Itene, and from GetMap. They will present on the exposure potential to nanomaterials, the wireless sensor and the platform. In the last webinar, we already spoke about biomonitoring studies where our colleagues from Unicentel, University of Lausanne and University of Torino presented. So that's already from my side. Of course, if you have any more questions on NanoExplore in general, feel free to have a look at our website where you can find all the details, or get in touch with us also on info@nanoexplore.eu. And with that, I hand over to my colleague Imma from Itene.
Okay, hello everyone. Thank you, Judith, for the introduction. So my name is Inma, I'm from Itene, and I'm going to make a sort of overall view of exposure potential to nanoparticles. Oops. Okay, right now. It is well known that particles are present in the air, coming from a wide range of sources, such as industry, vehicle emissions, wildfires, etc. There are a large number of works and papers about levels of fine particulate matter, PM2.5, PM10 in air. Ultrafine particles, understood as particles smaller than 100 nanometers with a chemical composition based on elements such as iron, potassium, copper, are also present in air. However, the literature regarding the environmental levels of these particles is quite limited. Ultrafine particles may be released into the air during accidental spills during production or later transport of these nanomaterials. They can also be generated in outdoor urban environments by automobiles, power plants, and urban-based industries. That's not working. Okay. Nanomaterials have unique properties. Due to their small size, they have a larger specific surface area and surface activity. Therefore, may result in different health and environmental hazards from those demonstrated by same materials but with bigger sizes. Besides, these nanomaterials, due to their large surface area, have a larger interface for chemical and molecular interactions, leading to a higher reactivity. According to literature, inhalation is the most common route of exposure to these nanomaterials. Again, due to the small size, nanomaterials can easily penetrate the respiratory tract and even reach the alveolar region, and they may cause some very important diseases such as asthma, bronchitis, or even cancer. In this sense, it is very important to know what are the levels of particles to which workers are exposed. The skin has also been investigated. However, most of the studies have suggested that there is no transdermal absorption of these nanomaterials. Since data for long-term human exposure is very limited, there is a need to develop methods to determine and better understand the effects of these nanomaterials. Nanomaterials can be released into urban environments and in indoor environments. They can be release into soil, water into the air. Since inhalation is the most common route of exposure for these nanomaterials, let's focus our attention into the presence of these nanomaterials into the atmosphere. As I have mentioned before, the main sources of these nanoparticles in the air coming from anthropogenic sources, vehicle emissions, smelter, power plants, or incinerators. Besides, there are also some natural processes that may be an important source of these materials into the atmosphere. Here in this figure, we have some examples, such as biomass burning, biogenesis, volcanoes, or breaking waves. These nanoparticles can be categorized in different groups according to their chemical composition. There are sulfates, nitrates, organic aerosols, sea salt, soot, titanium oxide, and other types of particles. When these materials are present in the atmosphere, generally they grow in size by condensation in the surface of other materials by nucleation or coagulation. Once they are large enough, they may be removed from the atmosphere by the rain or by dry deposition. These particles, depending on the chemical composition and morphology, they can also remain in the atmosphere as aerosols. The lifetime of these particles is short, normally from some hours to days, depending on the sizes. Aerosol is a term that has been widely used lately due to this coronavirus crisis. But what is exactly an aerosol? The definition says that aerosol is a suspension of fine solid particles or liquid droplets in air. Aerosol may absorb and scatter solar and earth radiation. They can influence the generation of clouds and heterogeneous reactions, and aerosol can also affect the abundance of distribution of the gases which are present in the atmosphere. As a result of these interactions, aerosols influence the Earth radiation balance, playing an important role in climate and global warming. As mentioned above, the highest exposure potential exists for workers at industrial facilities where these nanomaterials are produced, used, or handled. In this table, we can see some examples of levels of exposure to nanomaterials in workplaces for different activities. Here we can see the number of particles measured, the instrument employed, and if we take a look at the last column, we can see the scale of risk of exposure with a color, with different colors, where the boxes in red are the activities with high probability. At the right of the slide, we have an example of the release of particles when the process of melting nanoclide is taking place. We can see how there is a large increase in the number of particles when the action of melting this nanoclay begins. In this table, we have the levels measured in different indoor and outdoor environments. We can see also the different locations, the instrumentation employed, and the number of particles measured. For indoor environments, we have a level around 10 to 3 particles per cubic centimeter. And for the outdoor measurements, we have a wide range of concentrations. Sorry. How can we measure the exposure to these nanomaterials? Researchers in aerosol technology mostly use the types of instruments that are shown in this table. At the right of the slide, we have 2 pictures of 2 devices that are commonly used to monitoring aerosols. Here we have a CPC, a condensation particle counter. This device gives the total number concentration of particles. And the other image is an FMPS, a fast mobility particle size spectrometer, that gives the size distribution of the particles. However, only a few of these instruments are used to evaluate the exposure at industrial facilities due to the lack of field portability. Some of these devices are quite large and heavy, also because the complexity of use and high cost. Apart from the direct reading instruments that has been mentioned in the previous slide, we can also use some filters to analyze and to obtain the chemical composition of these nanoparticles. Depending on the type of nanoparticle that we want to study and the analytical information, we have to choose a proper filter media. Here we have some pictures of the filters that my colleagues have used in our facilities. Finally, in this graph, we can see the evolution of the total particles that are released when the process on nanoclay melting is taking place. There are the levels of particles measured with FMPS and with a CPC for near and far field. We can see how the level of particles increase at the same time as the process of melting is taking place, reaching a maximum value around 10 to 4 particles per cubic centimeter, which is a high value considered that we are monitoring in an indoor environment. And finally, it is very important to point out that the nanoscale opens the door to new or different potential risks on human health and the environment that are still not fully explored. There is an urgent need for information and data to extend the knowledge on the presence of these nanomaterials in the environment and workplaces. So for further information, feel free to contact with Carlos or with myself through these 2 email addresses. And thank you for attention.
Thank you very much, Emma. With this, I pass on to Pabla now from Raman.
Hello. So in my presentation, I will show you the prototype of the wireless sensor developed for the NanoExplore project, which should give the solution of problems which stated in my previously. So we will speak about its main features, the hardware, what we measure, and also I will present in tailored software, its function and its operation, and also the remote access to the instrument. Our wireless sensor is a modular system which serves for aerosol research or monitorization, and also as a tool for monitor personal exposure of nanomaterials. It is operated and controlled by tailored software by means of the human-machine interface. The system is portable, battery-powered, and can be connected to the internet. Our wireless sensor consists of 3 modules. The first one is a module for ultrafine particle measurement, which provides data of particle number concentration, average particle size, and lung deposited surface area. The sensors have a high time resolution, 1 second, and its accuracy is typically better than 30% comparing with reference systems. The second module of our sensor is the particle meter module, which provides PM1, PM2.5, and PM10 mass concentration. It has also high time resolution, 1 second, and it can measure even with high concentrations. The third module is for particle collection on filters or PM grids. The system is equipped with a pump with flow rate control. Here you can see the prototype of our wireless sensor. Its outer enclosure is a suitcase, so it's easily portable. The system is controlled by the touch screens. Here you can see the inlets of the modules, and here is the particle sample can be connected. And here are connectors for the solar panels if the system is used outside. So the software integrates the control and data reading of all modules. It permits to save data in files and send them to the server. There are two types of users, the advanced and normal user with different privileges. Data are labeled, so the user can distinguish between background measurements or exposure measurements. Some events which could disturb the measurement can be registered. And also automatic measurements can be programmed. And the system can be accessed remotely by from this web page. Then by entering the instrument ID, the user can log in and access to the home page of the software. And so it's the same screen which you see on the touch screen when operating locally and operating this remotely. So from this screen, the modules can be switched on and off, and the most important data are presented. Also, the container conditioning for outdoor measurement can be controlled here. Data labeling and the event setting is done here, and this part serves for give the nanoprevention information in form of traffic lights that show you if the threshold of concentration is overpassed. There are here the buttons which permit to save measured data in CSV file locally or to send them to the server. Here we can see the pop-up menu which permits switching between several other screens. So there is the data screen where all data of all modules are presented. You can't control the modules from this screen, only from the home page is possible. So this screen is for set advanced settings. There are several tabs for setting the GPS coordinations manually, the threshold setting for exposure assessment, UI set the data of server, and the saving and sending frequencies of the files. And also you can create and delete new users and program automatic measurement. There are up to 5 free text fields for comments and 5 fields to specify the measurement location and type of organization when the data are measured. So the screen serves for Wi-Fi connections, and in this screen you have status of all sensors. So when using remote access, you can use the file manager to view, download, or delete the files. So the files has an automatic name. which is unique, and it consists of sensor ID, date, and time when the measurement started. And so the measurement data are saved in these CSV files, and there are all information about the measurement. So there is the timestamp, the indication of time zone, the labeling of data, in the background, exposure measurements, and the events are also registered here. So that was our wireless sensor prototype. Thank you for your attention.
Thank you, Pavla. And now over to Doris.
Hi everyone, can you see my screen?
Yes.
Okay. So I'm Theodoris Vakas, and I will be presenting you the web-based platform developed in the NanoExplore context. We'll start with the scope of work and the goals of the platform, which was to develop a system able to handle data acquisition, management, as well as processing. The system should be developed based on principles of reusability and replicability in order to allow further exploitation of the project outcomes. For example, to be able to incorporate third-party data sources. The system should be developed on modern techniques based on API. I'm sorry. Be able to provide both analysis and visualization tools. Since it's a web tool with some of the data being not always public, it should also provide user and role management with the respective rights. So the system is composed from, let's say, three basic pillars: the data management module, the service module, and the web module. The data management is the place where all the data are handled, are acquisited from the sensors. They are ingested into the central database. The service application then, on its turn, speaks to the data and provides all the business logic regarding the requests being able to be supported in order to be visualized then in the web module, where's the place the end user interacts with the NanoExplore platform. In respect of data management, there has been we have been developing a modular schema based on international standards for observation and measurement. This schema has been implemented on with free and open source database management system, PostgreSQL. The main logic is it's really expandable. It's rather complicated in terms of being able to support different kind of data input, let's say. The main approach that worth underlying is that everything sensing is a thing. A thing might have one or more sensing instruments. So this allows to one station sensing more than having more than one sensing instruments. These sensing instruments produce data streams, which are collection of observations that we need then to visualize and analyze on the front end. Because of the data volume that's expected, that data from sensors are big data. We have been using timescale DB, which ensures a really nice performance and scalability of the system. Regarding the service module, as said before, it's based on application programming interface (API). It's developed from ground zero level. So there's flexibility in modifying and adding new operations and functionalities. It's based on the latest version of PHP programming language, and in the service module as well is where the user management module is living. The web module, it's still under development, but under refinement, I would better say. It consists of one module, a detailed data presentation with charts and predefined time aggregation based on time period selected by the user, allows time filtering, and of course for users with corresponding roles, it allows there's available an administration panel for the system where you can manage the users, the stations, etc. We will see some screens right after. So this is the home page of the web tool. We have tried to keep the logo and coloring scheme of the project. The content is also can be defined by the user in the administration panel. We have the map module where the stations are displayed as points, and there is also a time bar allowing navigation through the time. Here we have some example for providing aggregations and chart visualization of the values. In terms of statistics, it has been identified the need for min, max values, all the standard statistical measures, average, standard deviation, variance, correlation, and linear regression. Here's an example of visualizing some average values over stations. And here we have also incorporated the Copernicus atmosphere service into the tool as well. The resolution is not that detailed, but it provides a 3-day or so for forecast for different atmosphere parameters. So let's go to the admin panel, for which it's required to log in, of course. Here you can see different elements of the admin panel and the functionalities the user can access. On the left, So we have settings for the front page. We said earlier, you can modify the content, register new things and relate it with sensors. I remind that one thing might have one or more sensors. Register the observed parameters or properties. Manage the user, and also there is an alerting system for predefined users. Here's a screen from thing registration where you should and you can add the you can manually register as well a station with its location and add information about it. Here is the sensor list. Again, you can add manually or in case it's not through the automated procedure. The same thing for the observed parameters. Manual addition of user if he does not perform himself registration. User management in terms of changing his attributes, his name or contact details, and more importantly, his role in the system and if he is active or not. There is also an a work on accessing raw data and visualizing raw data and exporting them in for outside the system processing for example, where you can visualize at the same and at the same time different parameter different observed parameters, filter the data and export upon the user's will. And that should be all. Thank you very much for your attention.
Thank you very much, Theodoris. Yes, that's it already from our side. If there are no questions, we end the webinar here and thank everyone for attending. As I said before, we will send out the slides to everyone, and of course they will also be on the NanoExplore website. Thank you very much.